Hello and welcome back to the science class. Today we're going to be talking about the combined gas laws and kinetic theory of gases, also goes under kinetic molecular theory. So if we look at the pictures here, we're going to be talking about pressure, and we're also going to be talking about KMT and how gas particles behave as ideal gases. All right, so the molecular theory of gases. Composed of particles, these can be atoms or they can be molecules, and they have no attractive or repulsive forces amongst each other. These particles then move in random, constant, straight line motion. So because there's no attractive or repulsive forces between them, they're going to move randomly and they're moving in a straight line motion. We can see this in the previous slide. Notice how these particles are moving in straight lines to one another. Also, the third component is that all collisions are elastic. So that means kinetic energy is transferred without losing energy. So these gas particles are constantly moving without losing energy, considering that the temperature remains constant. Okay, so let's talk about particular gas laws. So there's one gas law, P1 V1 equals P2 V2. Now, this shows that the relationship between pressure and volume is inverse. So what this means is if we graph volume and pressure, then it would have an inverse relationship. So in other words, pressure decreases because volume increases. If volume decreases, pressure is going to increase. And the reason for that, let's just draw out a canister here with a piston. Now, excuse me, I do not have very good artistic abilities. Now, as the piston moves downwards, decreasing the volume, there's gas particles within here. Now, as I push the piston down, it's going to cause these gas particles to move closer together. Therefore, there's going to be more collisions with the walls of the container. And we know that pressure is defined as the force and frequency of collisions within the walls of the container. Let's talk about another relationship. P1 over T1 equals P2 over T2. This shows that pressure and temperature have a direct relationship. So as volume goes up, as temperature goes up, so does pressure. Now this makes sense because if we look at our model up here, the faster the particles are moving, because don't forget, temperature equals average kinetic energy, the faster these particles are moving, the harder the collisions are going to be with the container and more frequent they're going to be because these particles are moving faster. And remember, pressure is the force and frequency of collisions. Okay, our next relationship is V1 over T1 equals V2 over T2. So if we graph this, we'll see that there's actually also a direct relationship. So temperature, volume, as the temperature increases, again, it's going to cause these particles to move faster, and it's going to push the piston upwards, increasing the volume. As temperature goes down, the particles are moving less quickly. There's a loss of average kinetic energy. So therefore, there's not a large frequency and not a large force of collisions on this piston. So therefore, the piston is going to drop down. So the volume is going to decrease. Another way to think about this is a balloon. So if you ever put a balloon into liquid nitrogen or maybe some ice water, you'll notice that the balloon shrinks down. But if I put the balloon in hot water or boiling water, then the balloon's going to expand, most times to the point where it bursts. Now, for the New York State Regents exam, we can combine all of these laws together into P1 V1 over T1 equals P2 V2 over T2. So this right here is known as the combined gas law. And if you notice, it takes this relationship, puts it in there. It takes this relationship, puts it in there. And it takes this relationship and also puts it in there. Hence why it's called the combined gas law. So let's just try to do some practice on this. So A 2.71 liter of hydrogen gas has a pressure of 101.4 kilopascals. If the volume is increased to 3 liters, what will the new pressure be? Now notice they don't talk about temperature here. So if we go P1, V1 over T1 equals P2, V2 over T2, we can assume here that the temperature remains constant because it hasn't indicated any temperature change. So one way I like to solve combined gas law problems is to cross out the variables that remain constant. That way I can simplify things. So once I cross out the temperatures, then I'm left with one of the gas laws. P1, V1 equals P2, V2. Now all I have to do is plug in my variables so I can solve for it. So I can get 101.4 times 2.71 equals, and now we're looking for the new pressure. So we'll keep P2 as our variable, and we're going to multiply by 3.0. Okay, so if we solve this algebraically, multiply these two, divide by 3 for this, and I did the math for you. So we get P2 is equal to 91.60 kilopascals. Now, if you weren't aware, kilopascals is the SI unit for pressure. And don't forget, liters is the SI unit for volume. So if you see liters, milliliters, that's indicating volume. If you see kilopascals, maybe atmospheres, maybe torrs or millimeters of mercury, then those are all measures of pressure. Anyhow, this is our answer. So the new pressure is 91.60 kilopascals. Now this also makes sense if we look at our problem. Okay, let's move forward. So if 5 liters of an ideal gas is cooled from 24 to, negative 272 degrees Celsius, what will the new volume of the gas become? So first things first, let's write our formula. P1 V1 over T1 equals P2 V2 over T2. Okay, and what will the new volume of the gas? Well, we have volume indicated, we have temperature indicated. So let's assume that the pressures remain constant. So now my new formula is going to be V1 T1 equals V2 T2. Now, one thing to keep in mind with gas laws is that we have to convert all the temperatures into Kelvin. You can't do any gas law problems without using Kelvin. So, do you remember how to convert from Celsius to Kelvin? Well, hopefully you do. So we take the 24 degrees Celsius and we add 273. That's going to be our conversion factor. And now we're going to get 297. 297 degrees Kelvin. Now we get negative 272 degrees Celsius plus 273. Well, if we could do basic arithmetic, we know this is 1 degree Kelvin. So now these are our new temperatures. So if we look, T1 is equal to 297 degrees Kelvin. T2 is equal to 1 degree Kelvin. And we know this is very, very cold because 0 degrees Kelvin is equal to absolute zero, where no movement and particles whatsoever. Okay, so let's plug this in and see what happens. So we got 5 liters. I'll indicate units here. 5 liters over our T1 is 297 degrees Kelvin is equal to, well, we have 1 degree Kelvin on the bottom. And we're solving for V2 because it's asking for the new volume. Okay, let's cross multiply here. So we cross multiply. 5 times 1 equals 5. And now we get 297 V2. Okay, now we're going to divide both sides by 5. And now we get V2 is equal to, excuse me, divide both sides by 297. So you always check your work. V2 is therefore going to equal 0.02 liters. So it's pretty simple. All you're doing, if you're keeping up, is using the combined gas law, crossing out what remains constant, if anything, plugging in what you know and solving for what you don't know. So this is very similar to when we were doing heat equations, like Q equals MC delta T, Q equals MHF, Q equals MHV, all the same concept. It's a lot of algebra and chemistry. Okay, let's look at something different. So a 500 milliliter container is filled with helium gas at a pressure of 0.751 atmospheres. Don't forget, atmospheres is an indication of pressure, with a temperature of 25 degrees Celsius. If the volume is increased to 755 milliliters and the temperature is decreased to negative 56 degrees Celsius, what will the new pressure be? Okay, so let's get our formula up here. If you didn't know, for all my New York State Regents students, this is contained on table T. So in case you forgot, it's on table T. Okay, so let's take a look. We're indicating volume, we're indicating temperature, and we're also eating pressure. So all the variables in this combined gas law are being used. So that means we're going to have to plug everything in. But before we move forward, what units are temperatures in? Well, they're in Celsius. Should they be in Celsius? No, we need them to be in Kelvin. So let's convert them to Kelvin. So 25 degrees Celsius plus 273 is our conversion factor, equals 298 degrees Kelvin. Now, negative 56 degrees Celsius plus our conversion factor of 273 is equal to 217 degrees Kelvin. Okay, so now we have our T1 and now we have our T2. So let's start plugging in everything that we have. So if you look, initial pressure is 0.751. Our initial volume is 500 milliliters. Our initial temperature is 298 degrees Kelvin. Now, if we look, we're solving for the new pressure. So P2 is going to be our variable. Let's see, we're up to volume. So our V2 is going to be 755. And let's look at our temperature, which is 217 degrees Kelvin. Okay, what we're going to do again is cross multiply. And make it into a butterfly. Okay, so now we get 0.751 times 500 times 217 is equal to 298 times 755 times P2. Now, all we got to do is multiply across, find our variable, let's do some basic algebra. And I did the math for you, so P2 is equal to 0.36, and we need to indicate units here, atmospheres, because these are not in kilopascals. So now we have our answer. P2 is equal to 0.36 atmospheres. Double check our question to make sure that we solve for the right variable, and we did indeed, because it's asking for the new pressure. Okay, so that's it for the combined gas laws. Stay tuned for our next video, which is going to be on different gas law practice problems from the New York State Regents in the previous times. Enjoy.